We've learned how to compare the relative strengths of intermolecular forces in solids and liquids. But gases are going to be a little bit different because, by definition, a gas is a substance that has so much heat energy that it no longer is held together by its intermolecular forces. So, all gases are actually going to behave in the same way and according to the same four fundamental points. So, any gas we have, whether that be helium, hydrogen, oxygen, or nitrogen, or anything else, it's going to be a bunch of little particles zooming around at random. Sometimes they're going to collide together. Sometimes they're just going to stay apart. Sometimes they'll move a little slow. Sometimes they'll move a little fast. But the four main variables that we're going to be looking at whenever we look at a gas, it does not matter the identity of the gas, are going to be volume, which we'll represent with a V and measure in liters. Volume should be pretty self-explanatory if I've got a three-dimensional box here. Then that length by width by depth, that's going to be the volume of that box, okay? So then the other thing is going to be pressure, which we'll represent with a capital P, and we'll measure in either kilopascals or atmospheres. Atmospheres is a very convenient measurement because it's based on the idea that the Earth has a standard amount of pressure, and that we define as 1 atmosphere. Kilopascals is useful because if we take kilopascals times liters, we get energy, which is joules. If we take kilopascals, we also get to make a lot of metric conversions, so it can be very convenient, but it is by definition a Newton per meter squared. That's a terrible end. Let's rewrite that. So Newton per meter squared. So when we have pressure, we've got something like a wall here, and we're going to have these air particles, these molecules of a gas. Every once in a while, they're going to hit that wall. And when they hit it, they're going to ricochet off of it. And so when that happens, they're applying a little bit of a force. And that average force is going to be our pressure. Okay? The next thing is going to be temperature. We're going to investigate temperature more in thermodynamics, but temperature as a basic concept is going to be defined as how quickly these particles are moving around on average. Some of them will be slower, some of them will be faster, but the faster they're moving on average, the average of all those particles, the higher the temperature is going to be. That's what we really experience as temperature. Temperature is going to be measured in kelvins. And we represent it with a capital T. I broke my convention there. Let's go back and fix that. It's represented by a capital T, and we measure it in kelvins. Kelvins is the absolute scale for temperature. And what we define as 0 degrees Kelvin, which is as cold as it can possibly get. It cannot get colder. At 0 degrees Kelvin, all of these particles have just stopped moving. Everything's solid at 0 degrees Kelvin. This is going to be equal to negative 273 degrees Celsius. Okay? So if we want to convert from Celsius to Kelvin, we just add 273 degrees. We'll often get values in degrees Celsius because that's more convenient for us to measure, but our calculations have to use Kelvin. We cannot use Celsius. And then the last concept, I said there were 4, is going to be the actual number of particles, which is moles, which we represent with an N and measure it in moles. Simple enough. There is one other piece to the ideal gas law, because this is going to be an equation, and this is going to be a conversion factor. It's going to be a constant, and it actually shows up a lot in more advanced chemistry and in some physics. This R, this variable R, represents the universal gas constant. And there are a few different values for R. It is a constant. They're all the same value, but depending on which measurements we use, the actual number that we use in our calculations might change. For us, we're only going to use 2 versions of this because we're going to have answers in kilopascals or in atmospheres. If we use kilopascals to measure our pressure, then the value of R is going to be 8.314. And if we use atmospheres to measure our pressure, then the value of R is going to be 0.08205. Okay, so with that in mind, let's put this into practice. Let's say we've got something like a tire. We're filling up a tire. It's got zero anything in it right now. But we can have a volume, a total volume of 4.5 liters. So our tire can hold 4.5 liters of gas. It's going to be at a temperature, let's say it's a nice summer day. Let's say it's about 23 degrees Celsius. And then we're going to put in 4 moles of gas. And I want to know, what's the pressure going to be in both atmospheres and in kilopascals. So first off, we need an equation to relate all of these. That equation is going to be PV equals nRT. This is one of the most useful equations in chemistry and physics. You should commit this to memory. This should not leave your mind. It doesn't seem like much at first, but it's used in all kinds of calculations involving internal combustion engines, involving a lot of energy conversions when we're working with like steam turbines and things like that. This is an extremely important equation. Just doesn't look like much at first. So in order to use this, we just plug in our numbers. So first I want to figure out atmospheres. Okay? So I want to find the atmospheres of that pressure. So the pressure in the tire is going to be P times, and then my V is 4.5. And it's going to be equal to my number of moles, which is 4, times my R value, which I'm looking for atmospheres. So my R value is going to be 0.08205 times my temperature. Now, like I said, this is 23 degrees Celsius. We need this in Kelvin. So we need to take 23 plus 273. It's going to be 296. So we have 296 Kelvin. So then all we do is multiply these together, divide by my volume, and I get my pressure in atmospheres. So in atmospheres, I'm going to have 21.5. Is that right? 21.5? Yeah, 21 point, well, really round that to 6. So 21.6 atmospheres of pressure. Now, what about kilopascals? Well, I'm going to set this up the same way with mostly the same numbers. So for kilopascals. And I'm going to use a 4. And I'm going to use my universal gas constant for kilopascals is going to be 8.314, and then 296. This will be quite different. This will be a very different number. Okay, it'll be 2,187. This will be 2,187 kilopascals. And that should make sense because one atmosphere is about 101.1 kilopascals. Great. Let's do another practice problem. Now let's say I blew up a balloon, and it's going to be at a standard atmospheric pressure. Because the balloon flexes, it expands to equalize that pressure. Let's say I blew it up to a volume of, let's say 15 liters, a pretty large balloon. And it's going to be at, let's say it's a fairly cold day, 17 degrees Celsius. I want to know how many moles of gas do I have in that balloon. And so we're going to use our universal gas constant here too. And since I'm using atmospheres for my pressure, it's going to be 0.08205. So I just set up my PV equals nRT. You might hear people call this PIVNERT. I hate that word, but it's a useful way to remember it. So we've got 1 atmosphere of pressure times 15 liters. Number of moles is what I'm looking for. My gas constant is going to be 0.08205, and then my temperature. I need to convert this into Kelvin. So I'm going to take 17 plus 273. 290. It's going to be 290 Kelvin. So now I just take my 1 times my 15, and then I divide it by these two. So let's go ahead and do that. So let's take 1 times 15 divided by, put in parentheses, 0.8205 times 290, and my parentheses, and equals 0.63. So my number of moles is 0.63. Simple enough, right? All right. Now with that aside, let's look at some other applications of this. Because this is universal, what's really going to happen, if I've got a gas, let's just say I've got a balloon here, it's tied off right there. If I were to take this balloon and put it into a freezer, what's going to happen to the pressure and the volume and the other things inside this balloon? Well, since this equation, since it equals itself, what I can do is I can really divide both sides by my nRT. And then I would get PV equals nRT equals 1. So at any moment in time, any gas, if I take all of those variables and divide them all together, it's going to be 1. So it's always going to be that constant. So if I've got the volume of a gas here, and I call this my number 1 state, and I want to go, when it gets colder, number 2 state, I can just label all of these as 1s. The gas constant always stays the same. So I can say P1 V1 over N1 R T1 is going to equal P2 V2 over N2 R T2. Let's make that a little bigger. Now, if I do this, there's a couple things I can notice right away. First off, if I multiply both sides by R just cancels out. Boop, gone. Second thing, when I look at changes to a gas, I'm usually looking at them in a closed container, which means my number of moles is going to stay the same. So we can get rid of that too. And so when we do that, we get what we call the combined gas law, where we have this relationship, P1 V1 T1 equals P2 V2 over T2. And so let's put that into practice. Let's say I've got a balloon, end of my page there. Say I've got that balloon, and it's at a pressure of, let's just say it starts at 1 atmosphere. And it's got a volume of, let's say, 10 liters, just to keep things simple. It's got a temperature of, let's just say, 20 degrees Celsius, which is going to be 293 Kelvin. And I want to know what happens when I drop that temperature to, let's say, negative 10 degrees, which would be 263 degrees Kelvin. I'm going to look at my volume, and I'm going to look at my pressure. So if I just put it in the freezer, well, the pressure doesn't really change in the freezer. It's still atmospheric pressure, so it's still going to be 1 atmosphere. And so what I'm going to look for is my volume. How does my volume change? And so I can plug that into my combined gas law here. I've got 1 times 10 divided by 293 equals, and then P is still 1 times the V, V2, over 263. Now if I do that calculation, then I'm going to move my 263 over to the other side, and I'm going to end up with 263 times 10 divided by 293. And that will tell me my volume. So let's put that in. Let's use our calculator. It's 263 times 10 divided by 293. That gives me a volume of 8.9 liters. Okay, my volume becomes 8.997 liters. Simple enough. So this is our combined gas law. This is our regular gas law. We're going to need to be able to use these to solve all kinds of problems. Okay. Now there's one more thing that we need to keep in mind. We've now talked about a few different things we can do when we do stoichiometry. If I've got some kind of chemical reaction and I report my outcome in terms of a solid, I'm going to be able to report that in grams. Easy. I can just weigh that out. That's the most convenient way to measure a solid. We've looked at aqueous solutions now. That's going to be a concentration. That's going to be a molarity. If we look at liquids, sometimes it's going to be convenient to do grams. It's usually never convenient to do liters, but we can usually look up the density and figure out liters. For us, we're going to stick with grams. When we have gases, those liters can change. And so we need a way to figure out how many liters am I going to have of a gas? How many liters of a gas am I going to have? And for that, we generally consider our reactions to take place at something called STP. And that's going to be standard temperature and pressure. So what's our volume of gas at standard temperature and pressure? Well, if we keep standard temperature and pressure the same, and we call our pressure 1 atmosphere, and our temperature is going to be a 0 degrees Celsius, which is 273 Kelvin. Then what's going to be my number of liters per mole? Well, let's do that calculation. I've got PV equals nRT. My pressure is going to be 1. I'm looking for my volume. My number of moles, that's going to be 1. My gas constant, I'm using atmosphere, so this is going to be 0.08205. And then I'm using 273 degrees Kelvin. So we're just going to take that 273 times 0.08205, and that gets us 22.39. We round this to 22.4. 22.4 liters per mole. So now when we do stoichiometry, we have a way to report all of our different states. So going forward, whenever you're reporting the gas in stoichiometry, you're going to use standard temperature and pressure and use the 22.4 liters per mole. Okay?